So to solve a quadratic trigonometric equation, you need a 0 on one side and then factor. Like number 4 had the 0, and it was already factored for us. Okay, those are easy. Maybe there'll be one like that on the test. Here, well, you're going to have to actually, it has a 0 on the right, but you're going to have to do the factoring. And the same thing on problem number 6. Problem number 6. -2 sine squared x equals 3 sine x plus 1. Well, this problem is sort of like number 5. See if you can get it with a 0 on one side and then factor it. What could I do to get a 0 on one side and then maybe get something on the other side that I could factor?
Bring over
yeah, that's what I would do. Okay? I'm going to move this one over here. So I'm getting the 0 on the left. Hopefully that doesn't bother you. So it would be 2 sine squared x plus 3 sine x plus 1. I'll do that. I'm going to work this one out on this sheet of paper right here. Sometimes students say, oh, I don't like that 0 on the left. Okay, if you don't, just put it on the right. Equals 0. I'm going to try to factor this stuff. My college algebra class today, no one ever gets my jokes in there. I was writing a lot of stuff on the board in orange, and I said, I don't know what's making me want to write everything in orange today. And that no one got that it was a joke. Because I'm dressed in orange. I bought an orange shirt. I bought it about 8 months ago. I bought this shirt and thought, oh, I should wear this shirt for Halloween. So I bought it, put it in the closet, tag still on it. This morning I saw it, 5 o'clock when I'm getting dressed. I'm like, oh wow. I put it on and thought, well, it's still harvest season. And then my brother was like, well, if you're going to wear that, you're going to have to change your belt. I was like, no, I think I can wear the belt I was wearing. And he said, no, I think you changed your belt. Yeah, I did change belts. So I'm all in orange today. Did I talk long enough for you to get this thing factored? Or when I'm talking, do you stop working? 1 and 1. What do you think I'm going to put in the first positions to get the 2 sine squared x? Maybe would it be a 2 sine x and sine x? And both plus. So did I factor this thing correctly? So 2 sine squared x, 2 sine x plus 1 sine x, 3 sine x. 1 times 1 is 1. Second sine was plus, so 2 of the first. Then set each one of these factors to 0. If I set 2 sine x plus 1 equal to 0, I'd move the 1 over and divide by 2. Can I do that all in one step? Sine x equals -1/2. Setting the sine x plus 1 equal to 0, move the 1 over. Sine x is -1. And are we ready to look at the unit circle? Are y'all caught up with me? Let's see. So I'll do the purple first. Where's sine equal to -1/2? Sine would be -1/2. It's going to be here towards the bottom, isn't it? sine is negative 1/2 at 210 or 330 degrees. So 7 pi over 6 or 11 pi over 6. How are we told to do this one? Still in radians. Eventually there'll be some that say write it in degrees. So 7 pi over 6 and 11 pi over 6. 7 pi over 6 and 11 pi over 6. Those are the purple solutions. By that I mean those are the solutions to the purple equation. And what about the blue solution? Sine x is negative 1. Where's sine negative 1 at 270 degrees? 3 pi over 2 would be the solution to the blue equation. Any questions there? This is solving quadratic trigonometric equations. So 7 pi over 6, 11 pi over 6. Do some of y'all do this where you print out your homework, work it out, and write down the answers, then go type it in later? Or none of y'all do that? No? Sometimes? Okay.
Like if you're at work and you can get on the computer.
Oh yeah, that's a good, yeah. Let's see. Number 7. Let's do number 8. Number 7. It's already factored with a 0. This one's very much like number 4. Just set each one of those to 0. Okay. Let's do number 8 instead. Here we start getting to the stuff y'all love. What's y'all's favorite part of trigonometry? Starts with an I. The identities. Oh wow, y'all are so smart. Starting with number 8. You might have to use an identity here. How are we doing on time? 2 sine theta plus 1 equals cosecant theta. Ooh. Generally, if it's already factored like this and it has 2 separate trig functions, that's okay. But generally, you sort of want the same trig function, if that's possible. And this number 8, 2 sine theta plus 1 equals cosecant theta. Is there a way I could rewrite cosecant theta so that it involves a sine theta? Yeah, if we think of it as 1 over sine theta. So the first thing I'm doing is rewriting that cosecant as 1 over sine theta. You might be thinking, oh, this looks bad. You made it look even worse now. But now let's get rid of the fraction. What would I need to do to get rid of the fraction there? Yeah, multiply both sides by sine theta. That's right. So I'm just going to multiply both sides by red sine theta. And over here, you distribute over addition or subtraction. Here, the red sine theta and that black sine theta cancel, leaving just a 1 on the right. This problem's going to start looking sort of like number 6 in a moment. Or at least similar to it. When I distribute this red sine theta, I would have 2 sine square theta, then plus what? Plus another sine theta equals 1. Is it now looking sort of like number 6? Well, 5 and 6. We need a what number on one side? Do we need a 0 on one side? Yeah, so I'm going to subtract 1. That's what that means, subtract 1. So here's what I'm going to try to factor. 2 sine squared theta plus sine theta minus 1 equals 0. 1, 1. The 1 times 1 gives 1. What am I going to put in the first two positions? The two first position places here. Not just a sine theta and a sine theta. I would need to put a 2 sine theta on one of them. And just a sine theta on the other. And how do I arrange, since this is going to be a negative 1, there needs to be a plus and a minus. How should I arrange it? It's going to take a little thought. A minus here and a plus there. I think that's right. And for those of you that don't know my little bizarre language, if I say I think that's right, that means that's right. The negative 1 sine theta plus 2 sine theta is a positive 1 sine theta. Any trouble with this factoring here? And then set each one of these factors to 0. Oh, I'm running out of room. So when I set 2 sine theta minus 1 to 0, and sine theta plus 1 to 0, let's see. How would I solve this? I'd move the 1 over and divide by 2. Can I do that all in one step and say sine theta equals what? 1/2. For the purple solution, I'd just move the 1 over, wouldn't I? Sine theta is minus 1 or negative 1. Y'all caught up? Any questions? So let's see. I need to know when is sine 1/2. That would be the red answers. And then where's sine negative 1? Okay, sine would be 1/2, 30 degrees and 150. Now this is one where the instructions say 0 degrees to 360. So you're going to type your answer in degrees. You don't put the degree mark, okay? Just, you're going to type in what? What do you say, 30 degrees and 150? So you just type in 30, comma, 150. You don't put the little degree mark. What about the purple solution? Sine theta equals negative 1. That would be 270. Okay. Any questions there? The circled answers, those are the answers to problem number 8. Where it says the solution set, you would type in 30, comma, 150, comma, 270. The order in which you type them in doesn't matter, of course. Those are the solutions between 0 and 360. This seems like a good time for me to mention something. These are only the solutions between 0 and 360. They're not all of the solutions. Why do I say that? Well, if we took 360 degrees and added it to 30 degrees, we'd be 390. Isn't this, and that at 390 degrees, would the sine of that 390 be 1/2? If you looped around once, as long as you stopped here, wouldn't that angle be a solution? Theoretically, you could loop around as many times as you want. There's going to be some problems that say, write all the solutions, not just the ones between 0 and 360. If it said to write all the solutions, write all solutions, you would do it like this. You take each one of these three And you need to somehow algebraically write on there or add any multiple of 360. Why am I saying 360 degrees? Well, 360 is a loop. If you wanted to add 720, 30 degrees plus 720 degrees, that would be 750. It'd still stop here, right? 750 degrees. Do you remember how those angles bigger than 360 work? You loop around once, loop around again, and still stop here. And the way we do that is we're going to say 30 degrees plus any multiple of 360. I'm writing 360 degrees in. And this is where n is some integer. It's counting how many times you loop around that unit circle. 150 plus 360 degrees in. 270 degrees plus 360 degrees in. If it said write all the solutions, and there's going to be one like that in a moment, you just stick on plus 360 degrees in. What if it weren't in terms of degrees? What would you stick on there? Okay, yeah, and so radians, So instead of 360 degrees, what would you put? 2 pi. And there's nothing special about n. It might use the letter K or J. Okay. And we'll see that in a moment. But not on number 9. Number 9 says solve it over the interval 0 degrees to 360 degrees. Tangent theta minus 3 cotangent theta equals 0. If there's two different trig functions, you want to be able to somehow factor it so that they separate, like number 7 is factored and the two different trig functions are separated. Here on number 9, really no way you can just immediately factor it in such a way that you have tangent in one place, cotangent the other. So what am I thinking in mind? Keep it in mind that up here I'll replace cosecant with 1 over sine. I have any ideas of maybe what I'm going to do on number 9? What am I hinting that we replace? I'll watch how I'm putting it. We rewrote cosecant as 1 over that. What am I trying to say we're going to do with cotangent?
You're going to use trig identities.
And write it as 1 over tangent. Okay? I'm going to get this all in one trig with one trig function by, we have tangent theta minus, I'm going to think of that cotangent as 1 over tangent, so it would be 3 over tangent theta equals 0. Now, any ideas what I'm about to do? Sort of on number 8. What did we do on number 8? After I rewrote cosecant as 1 over sine, I then got rid of the fraction. There's sort of a pattern here. What do you think I'm going to do now? Multiply 3 by tangent theta. That'll get rid of the fractions. So we would have a tangent theta times tangent theta. That would be tangent square theta. Then a minus the 3 over tangent theta times tangent theta. Is that just going to give me a 3? Equals 0. Now we can solve this thing for tangent theta. First of all, solve for tangent square theta by moving the 3 over. And What am I going to do now to get rid of that square? Square root. Just the positive square root? Am I just going to say positive square root of 3 or plus or minus? So we're going to have to look at the unit circle and figure out where are we getting all of those plus or minus square root of 3 for tangent. If you find the one in the first quadrant, it's just the corresponding ones in the second, third, and fourth quadrant. We're looking just at the first quadrant. Where are we getting, if you go sine over cosine,
60.
is it at 60? Sine over cosine, is that going to give you a positive square root of 3? So it's all the over 3 ones. So 60 degrees, 120 degrees, sine over cosine. Is that giving me a positive or a negative square root of 3? That's a negative. What about down in the third quadrant, the other over 3 one? 240, sine over cosine. That's a positive, isn't it? And in the fourth quadrant, sine over cosine, the other over 3, the 300 degrees, that would give me negative square root of 3. So it's 60, 120, 240, and 300 degrees. Any questions there?
We're doing this 60, 120, 240, 300 because it's a plus and minus, right?
Right. Because why, like at 60, positive over positive, that gives you positive square root of 3. At the 120, that would be positive over negative. That's giving you the negative. Then move into the fourth quadrant.
I understand the answer.
Uh-huh.
I just, my question.
Oh, you're wondering why we did the plus
Right,
minus?
it's because of the square root.
The square. When you take that square root, you're taking the positive and negative. And that's consistent with what you did in algebra classes. If you had something like in algebra, if you were solving something like x squared equals 49, there's not just one answer there. Sometimes students will say 7, and I'll say, okay, there's positive 7, and what else? What other number could you square to get a 49? Negative. Okay? So when you're taking the square root, when you're dropping that square, you're taking the positive and negative square root. Okay? So that was 9. Let me see. I'm going to jump up into one like number 16. Because this one looks really messy. Problem number 16. Well, I'm glad that part of the thing isn't recorded. Okay, so number 16. Cosine pi plus x plus sine x minus pi over 2 equals 1. This is a really good equation. Why am I saying it's really good? Well, it's going to have to use something that we did a while ago. You don't? Oops.
Angle identities.
Yeah, those sum and difference identities. For cosine pi plus x, you don't just distribute the cos and the sin. For cosine pi plus x, you go, do you remember those sum and difference identities? For cosine, it looks like this. Cosine, cosine, change, sine, sine. So I'm distributing the cosine pi, or I'm expanding the cosine pi plus x, and I'm doing it in blue. Cosine, cosine, change, sine, sine. Cosine, cosine, change, sine, sine. Notice I'm going pi x, pi x. This plus I'm about to write down is that red plus I just circled. Now which identity am I about to use for sine x minus pi over 2? Well, to expand sine x minus pi over 2, it's sine, cosine, same symbol, cosine, sine, equals 1. That equals 1 is the equal 1 here. Sine, cosine, cosine, sine, same symbol in the parentheses, x pi over 2, x pi over 2. It's really messy. It's going to start simplifying really nicely. 16 and 17, these work out real nice. Replace the ones that go through, and the trig function that don't have x's, look that up on the unit circle. Like cosine of pi. What's cosine of pi? Cosine of pi would be -1. So I'm going to replace every cosine pi with -1. That's right here. What about the sine of pi? What's the sine of pi? Yeah, it's 0, isn't it? So we have a -1 times cosine x. Then a -0 times anything's just 0. Then I'm up to the red plus. What am I going to look up on the unit circle? What angle? Pi over 2. So cosine of pi over 2 is a 0. Sine of pi over 2 is a 1. So this thing, sine x times 0, that's just 0. Minus cosine x times 1. Let me just write it neatly. What do we have remaining here? We have a -1 cosine x. So all of this is 0. All of that's going to be 0. Sine x times cosine pi over 2. Sine x times 0 is 0. So we have -1 cosine x minus 1 cosine x. Could I combine those as -2 cosine x equals 1? Divide both sides by -2, and are we ready to look at the unit circle? We have 1 over -2. So where is cosine -1/2? So that would be over in quadrant 2 and 3. So let me see. Quadrant 2 and 3. Where's cosine -1/2? 120 degrees, or 2 pi over 3. How are we told to do this? Yeah. In radians, 0 to 2 pi. So 2 pi over 3 and 4 pi over 3. Any question? Let's do number 17. My brother's going to be like, please tell me you're joking when I tell him about the scissors and stuff. He's like, please tell me you're joking. You're not sitting up there cutting the paper so it lays flat there. Which is what I'm doing. Oh, wow. Let's see. I guess there's a lot of wrong ways to do this one, probably involving distributing SIN. You can't distribute SIN. You can distribute sine x or sine theta. But you can't just distribute the SIN. How do you expand it? Well, sine cosine, oops, same symbol. So this is a plus. Sine, cosine, cosine, sine. Sine, cosine, cosine, sine, same symbol in the middle. There's another one of those little phrases I'll be saying. Plus. I do the same thing, sine, cosine, cosine, sine, same symbol in the middle, so it's going to be a little different. Let's see, what color will I use? Sine, cosine, cosine, sine, and we have equals 1. Is all of that showing there? Oh, equals -1. Sorry, thanks for pointing that out. It's a -1. So sine, the blue stuff is what's my expanding this? Sine x plus pi over 4. Purple stuff is that. Sine x minus pi over 4. Now, before we even start looking at the unit circle, some of this stuff will subtract out right off. Which stuff can I mark out?
Cosine x sine pi over 4.
Yeah, that cosine x sine pi over 4 minus cosine x sine pi over 4. And then the stuff that's remaining, I could go ahead and write those as, this is 1 sine x cosine pi over 4 plus 1 sine x cosine pi over 4. I'm going to write that as 2 sine x cosine pi over 4 equals -1. Is there something I can look up on the unit circle there? Oh, well. When I say that, I don't mean, I suspect all of y'all have that memorized, right? Cosine pi over 4 is square root of 2 over 2. So I can replace this cosine pi over 4 with square root of 2 over 2. In fact, I'm going to sort of change the order up. I have the black 2. Then I'll go ahead and write times square root of 2 over 2, and then sine x equals -1. The fact that I've sort of reversed the order, multiplication's commutative. A times B is B times A. So I haven't really changed anything. The 2's cancel. Oh, I'm through with this unit, so, oh wow, not play with it. So to get the sine x completely by itself, I would divide both sides by square root of 2, So we have sine x equals -1 over square root of 2. We don't normally write it like that. Can y'all rationalize this in your head by now? -1 over the square root of 2 is the same as negative square root of 2 over 2. So let's look at the unit circle. That's going to be in the lower half, isn't it? Where, I'm going to look and see, where is sine negative square root of 2 over 2? It's going to be at the over 4s down here. At 5 pi over 4, and where else? At 7 pi over 4. So the answer here, pi over 4, oops, 5 pi over 4, sorry, and 7 pi over 4. Okay. Sort of like those two problems, because when you get your review sheet, this is in the face-to-face class, not online, but when the face-to-face class gets the review sheet, they'll see the software makes these problems and regenerates them very nicely. Okay? So you can almost be guaranteed you're going to have something like that on the third test. Software makes some really nice ones. Oh wow, let's look at this. At number 13. Says, solve this equation. What all is it saying? in degrees for all exact values. Notice what's missing here. None of that 0 to 2 pi or 0 degrees to 360 degrees. Here it's saying find all the solutions, and you'll see it's that little, notice how it has the plus 360 degrees in stuck on at least 3 of them. Okay? One of them has plus 180 degrees in. This is number 13. Get started. It's number 13. 2 sine theta equals 2 cosine 2 theta. Well, why did I change the color here? I think that I could divide both sides by blue 2, and that'll get rid of these 2's here. The first 2 problems in there. The first 2 2's in the problem. It doesn't get rid of this last one, the one that I put in red. If I just divide by 2, the equation I'm going to try to solve is sine theta equals cosine 2 theta. Well, here we have 2 different trig functions, sine and cosine. And hopefully on the right-hand side, that cosine 2 theta is bringing something to mind. That's the double angle identity for cosine. We had 3 of those. Cosine squared theta minus sine squared theta is one of them. The other one, 1 minus 2 sine squared theta. And the third one, 2 cosine squared theta minus 1. When I see cosine 2 theta, that sort of brings to mind those double angle identities for cosine. And I start thinking maybe, you see, I've got to write everything. I really need either sine theta for everything or cosine theta, one or the other. Which one of those could maybe we use? What would this, that 1 minus 2 sine squared theta? If we replace cosine 2 theta with 1 minus 2 sine squared theta, is it going to turn out to be something similar to something we've already done? This equation here, if I replace cosine 2 theta with 1 minus 2 sine squared theta, I think it's similar to now, just an equation we've already solved. Is it a quadratic equation? Yeah. Let's get a 0 on one side and factor. This is one of those times I'm going to move everything to the right. No, to the left. Because I always like this first number to be positive. 2 sine squared theta, then a plus sine theta, and what would it be, plus or minus? Minus 1 equals 0. You'll see how we took an equation, used an identity, and rewrote it so it looks like an equation we know how to solve. Could y'all draw the 2 sets of parentheses and get this factored? Well, you can at the very least get started on it by filling in the 2 last positions. 1 times 1 is going to give us 1. What would I put in the first positions? 2 sine theta and sine theta? Now, the second sign is minus, so there should be a plus and a minus. How should I arrange it if I want a positive sine theta? If you're uncertain, try one way, and fill it out. If that doesn't give you the positive sine theta, reverse the sign.
Minus 1 plus 1.
If I put a minus 1 and a plus there, does that do it? I would have a -1 sine theta. That's the little mark I just made. That's when I'm doing FOIL, first, outer, inner. And here's the last. That would be a +2 sine theta. I sure think this is right, isn't it? -1 sine theta plus 2 sine theta is a positive sine theta. So set each one of these to 0. Might even be one we've already done. Here we'd have in red sine theta equals -1. Over here, move the 1 and divide by 2. Sine theta is 1/2. So let's see. Oh, let me move it up a little. 30 and 150 degrees. That would give you the sine equal 1/2. For sine theta equal -1, 270. So 30 degrees, 150 degrees, 270 degrees. But this is multiple choice here. And remember it says find all the solutions. So that means put a +360 degree in on each one of them. So let's see. Which one? Is big enough that y'all can tell which answer it is? Do I need to magnify it a little? Let me see. 31. Is it B? It's B. 30 degrees, 150, 270. Oh, do we have time to do number 14? Maybe not. We're going to have to do it super fast. Okay, so it's basically the same type of problem. You're going to have to replace cosine. You're going to have to replace the cosine 2 theta with a 1 minus 2 sine squared theta. So this is going to look a little messy. Replacing this with 1 minus 2 sine squared x, not theta. So here's the equation. 1 minus square root of 2 sine x equals 1 minus 2 sine squared x. I used that one so that we have the same trig function. Now let's move everything over to get a 0 on one side. When I do that, it'd be a positive 2 sine squared x. Then we have a minus square root of 2 sine x. Hey, what's happening to the 1s? Yeah, so we just have equals 0. The tricky thing about this one was to know, replace that cosine 2x with 1 minus 2 sine squared x. Why did I choose that one? Because there was a sine x here. If yours regenerates with a cosine x right here, what would you use? 2 cosine squared x minus 1. So these can regenerate a little. They can't regenerate a lot. Okay. Let's see. Now, I guess we haven't done one like this. There's not a constant term, so that's going to be the easy factor. Just factor a sine x out of each of those. If I factored a sine x from each of these, it'd be a 2 sine x minus square root of 2 equals 0. And I'm doing this fast now. So I'll move the square root of 2 over and divide. So I'm looking at where's sine x equal to 0. That would be at 0 and pi. Yeah, it says write it in radians. So I'm just without pulling up the unit circle. 0 and pi is where sine x is 0. Where sine square root of 2 over 2, that would be at pi over 4. And 3 pi over 4. So, So, this says, find all the exact values. So, 0 plus 2 pi n, pi plus 2 pi n, pi over 4 plus 2 pi n. Ooh, why didn't y'all tell me I'm at? And 3 pi over 4 plus 2 pi n. I'm thinking it's going to be C. We're out of time. Let's see, 2 pi, 0 pi, pi over 4, 3 pi. Yeah. Okay. We're out of time. I'll see y'all next time.